astronautics. I'm not going to go into that. If we have any time today, I'll go a little bit into a slightly different but related topic. But if we don't have time, that's okay. I shared with Diane a PDF file of all the slides that I will be presenting today. So you don't need to take pictures or memorize anything, because you will have the PDF. And Diane told me that she has received it. So feel free to also contact me after this talk if you want to clarify something isn't clear, or maybe you want to apply something, implement something in your own class, and you want my advice. I'll be very happy to do so. So I'm going to start by sharing my screen. And I was told I have 40 minutes, 40 minutes just for the talk. Is that still the case, Diane?
Yeah, you can talk for 40 minutes. We are on time, actually. But I don't think we're going to have time for the Q&A session at the end.
Okay. So I'm going to try and present in less than 40 minutes, just to give some time if people have questions. I see that in Google Meet, when I do a presentation, it also shows the slides on the side. I don't really want to do that. So what I'm going to do, I'm going to share my PDF. That should be okay. So I'm going to do that now. Okay. So I'm now presenting a PDF file. If you cannot see what I'm talking about, please let me know. And all I can see is my screen, is my presentation. I cannot see myself. I cannot see anything else. So anything isn't clear, anything is going wrong, please let me know. So I will start now. So what I'm going to cover today is, first, why is systems thinking important? Why is this a topic that I research and teach and talk to people about? And why should you spend any time listening to me talk about it? So what is the motivation for this talk? The second is, what is systems thinking? Of course, this question is a very big academic question, and we can talk about it and debate, and discuss it for months if we want to. But I'm going to provide some definitions just so we can have this conversation. Then most of my presentation will be about how. So how do you teach systems thinking? Describing systems, designing systems, and connecting systems. How can you teach this to students? And if we have any time, I'll talk about another topic. If we don't, it is in the slides, and you can always get back to me afterwards. By the way, my email is here, realavi@mit.edu. Feel free to just contact me, like I said. So going into the why of systems thinking, there is a term called VUCA, V-U-C-A, which is about the world that we live in and have lived in for the past few decades, which is volatile, uncertain, complex, and ambiguous. And this is the world that our students are going to be joining, whether they go in, and get a job, or whether they start their own business, or whether they join a government organization, or whether they do something else, they go into academia, or whatever they do. This is the world that we all live in, and this is the world that we are trying to prepare them for. And this kind of world requires skills that we don't always teach at school and at university. And one of them is systems thinking. Systems thinking really helps with all of these things, but especially with complex phenomena, complex problems, complex situations, complex scenarios, complex organizations, and so on. And this is recognized by organizations, international organizations, national organizations, economic, educational, scholars, researchers, that systems thinking is a very important skill, one of the most important skills for the time that we live in right now. And of course, when we talk about systems thinking, now we are moving to definition. Now we are moving to what? When we are talking about systems thinking, we are not really talking about, you could say some things are systems and some things are not systems, but some systems are more definitely systems than others. So it's probably more of a spectrum, I would say, is a more useful way of looking at it. So we have simple systems. If, for example, you take a bicycle, just a regular bicycle, not with gears and all kinds of technology, just a regular old bicycle. It's a simple system. And this is the kind of system that we would probably want to start with if we are teaching systems thinking. We don't want to start with something very complicated, like the refrigerator. I'm sitting now on a mini refrigerator, so it's quite suitable that I'm giving this example. But a refrigerator is a more complex system, especially a refrigerator that has temperature control and sensors, and all that kind of stuff. And finally, we have complex systems. And the system does not have to be technological. A system can be biological, it can be technological, can be social, or it can be a combination of those things. So a human being, a person, something that has personality is a complex system. A bicycle does not have personality, right? A bicycle is a lot more predictable. We know what a bicycle can do. We know what a bicycle cannot do. When a bicycle breaks down, we can usually quickly identify the problem and fix it. Even with a refrigerator or let's say a car, which are much more complex than a bicycle, it may take us time. We may need a special person, a specialized, expert, like a technician, to come in and fix it for us and identify the problem. But it's perfectly possible, and it's overall quite predictable. It's just as a very large number of elements. But with people, it's a different story, right? With organizations, it's a different story. Sometimes people do things we don't expect, we didn't even think they could do. Sometimes people fail to do things that we expect them to do. It's not always easy to identify exactly what the problems are. So this is just a useful spectrum to think about when we think about systemness, how much of a system something is. And we kind of add more and more and more properties. So now I want to talk about the difference between technological systems and natural systems. So a technological system, we can say very simply, has a structure and a function and a purpose. So if we go back to a bicycle is made up of parts that interact with each other and connect to each other in a certain way. A bicycle also has a function. It's not just, standing there doing nothing. It's supposed to take us from one point to another. It's supposed to roll on an appropriate surface. There are certain physical forces that allow it to function, and so on. And finally, the bicycle has a purpose. It's used for something. It doesn't just function. It doesn't just take us from A to B. It has a purpose, which is to take us from a place we are at to a place we want to go to take us on specific types of paths, right? A bicycle cannot just go everywhere. It also helps us get exercise. It helps us not pollute the environment. It helps us go a lot faster than just walking, right? So it also has a purpose, and the purpose is where it connects to people, is where it is relevant to people, to human beings. The structure and the function, maybe we care, maybe we don't care. The purpose is what we really care about when it comes to technological systems. Every technological system ultimately solves a problem or provides some kind of a need, fulfills some kind of a need for us. It's not there just because it's there. But this is not true for natural systems. So in this way that we are thinking about it, in this sort of scientific way, there is no purpose to a natural system. So the tree is not there to give us wood or to give us shade or to absorb carbon dioxide and help the environment. It does all those things. But in terms of purpose, what we talk more about is outcome. Because we say, okay, this outcome is beneficial for us, or we care about this outcome of the function of the tree. But this does not mean that we designed the tree to do this. It simply does this. So the difference between technological and natural systems is that technological systems have one or more purposes, and they are designed for that purpose. And sometimes they may fail. Sometimes they may not achieve the purpose. But they're supposed to have a purpose, whereas a natural system does not. It has an outcome or a number of outcomes that we may or may not care about. Now, to the teachers out there, if any of you have heard of Bloom's taxonomy of learning, where we have these very sort of more basic thinking going into more advanced thinking, and we kind of need the basic thinking to build a more advanced thinking. So we need to have knowledge, and we need to understand, and then we need to apply, and then we can analyze, and then we can synthesize, put things together, and then we can evaluate our own work or other people's work. There is also kind of a revision or renewal of this taxonomy, which you can see on the right, which is using not nouns but verbs. So it's using actions, but it's quite, and this is done by Anderson, sorry, but it's quite similar. The ideas are quite similar. But what I wanted to show you here is that systems thinking is definitely an advanced thinking skill. It's what's called a higher order thinking skill, because it requires all those things at the bottom. So synthesizing different things that we know and creating new things, these things involve systems thinking. So systems thinking is not something that you can just do with, without knowing anything about a topic. You do need to know some things before you can start really doing systems thinking. And again, when I say higher order thinking, there are different types of higher order thinking skills. There's not just systems thinking, there's also creative thinking, critical thinking, algorithmic, recursive or algorithmic or computational thinking, metacognition. There are different types. But what's common to all of them is that they are complex. They are not algorithmic, which means it's not just a recipe. It's not just an equation that we learn an equation and now we can apply it, right? It's higher than application. We can generate many solutions, and it depends on self-regulation. So it's not enough that you just learn how to do something with systems thinking. You need to go back and see what you did and think about what you did well and what you didn't do well, and then try and improve. So you need to be, as a learner, as a student, you need to be aware of how you're approaching the problem and how you're applying systems thinking. So again, this is just to say that systems thinking is a higher order thinking skill, and it's not one of the very basic thinking skills that we need for basic learning. It's a bit more advanced, and it needs to build on top of existing knowledge that students already have. So now, what is systems thinking about technological systems? Because you can have systems thinking about natural systems and different types of systems. Now, I want to say, when I say technological, I developed the framework that I'm going to present to you in the next page. I developed it mainly for engineering students in their first year, but it is applicable for any artificial system. So for example, a university. A university, is not a natural system, right? A university does not exist in nature. It includes natural systems, it includes people, and it includes technological systems, and it includes social systems. But overall, it is not a fully natural system. So this can also apply to that kind of system. So what is systems thinking about technological or artificial systems? So it is the ability or a set of skills that allows you to describe and explain and predict and control every aspect of the system, but also how they interact, how they relate with each other, and how different systems interact and relate with each other. And I will explain what all of this means. But if somebody has all of these abilities to the maximum degree, they are an expert in systems thinking. And by the way, I don't think that I have all of these abilities. So to achieve expertise, is something that takes a very long time. It's not necessary to be a full expert to benefit from systems thinking. But this is kind of a full definition. This is not for the beginner. Now, there are obstacles, there are challenges and difficulties with teaching systems thinking, and definitely in first-year education, which was my situation in 2022 when I developed this framework. So first, you want a pedagogical framework, a way of teaching that you can foster systems thinking, you can develop systems thinking or promote it or improve it. You can teach systems thinking, but you can also assess the systems thinking of the students. Because it's not enough to just give them an assignment and then assume that they are going to develop systems thinking. You need to check, you need to assess and see whether they've actually improved or learned about systems thinking. Another thing, it needs to be appropriate for novices. So these are students in their first semester, first year, and they don't have any expertise in any discipline yet. They learn things at school maybe, but they haven't really started their degree. And at MIT, students choose their degree at the end of the first year. They are there for 4 years. They choose their degree at the end of the first year. So when I have my students, first year, first semester, one could become a biologist, another one could become a chemical engineer, another one could become an economist. I don't know. It needs to be domain agnostic for that reason. So it cannot be specific to one domain, because I should say there are other frameworks of systems thinking to teach systems thinking. But I could not find one that was appropriate for these 4 points. And finally, it needs to be scalable and adaptable to various learning objectives. So not something that is very, very narrow and is only good for 1 or 2 types of assignments. I wanted something that could be relevant for a lot of disciplines, for not just for first year, by the way, for even third year, fourth year, even graduate students, but definitely good for novices, but something that I can scale up, that you don't need me to teach it. Now, this is probably the most important slide in my whole presentation. This is the framework. This is the construct that I came up with. And there are 2 papers that I published specifically about it with full explanations and details and how to do assessment and everything. So if there is just one paper that you maybe want to check out, and this is free, so as long as you have internet access, you should be able to find it. And there is a references slide at the end with all the full references. But this one here, Levy and Brogat-Bertel 2024, is the best one if you want to really get an understanding of this framework beyond what I'm going to talk about today. And this framework is called SAFO, S-A-F-O. S-A-F-O stands for System, Architecture, Function, and Outcome. So this is the words to remember. So first we have our system of interest, which needs to be technological or artificial. So that's in the center. This system has an architecture. So it has structure and behavior. So it's made up of parts, and these parts interact with each other in cause and effect. So maybe there is matter going back and forth or just one way, energy, information, some interaction. And we have a function of the system. And on its own, the system doesn't function. If you think about a bicycle on its own doesn't do anything, right? It doesn't function. It needs somebody to drive the bicycle, and it needs a surface to roll on. If it cannot interact with those 2 things in the right way, it will not function. So the function goes into the boundary systems, the other systems it's getting input and output from. Our system of interest is getting input and output from. And finally, we have the outcome. The outcome is the so what, or why do we care? The outcome is, how does this affect people? What problem is the function solving? Who is being helped? Who are the stakeholders of the problem? How are they benefiting from the system? And finally, another important thing to think about is detriments, negative effects of our system. So every system that we use or design or try and improve or just describe doesn't only benefit people. It also causes some kind of detriment, whether it has a cost, or it requires resources, or it causes pollution, or it may cause accidents, or it could have different detriments. But this is also very important to think about, because part of understanding systems thinking, this is what I am claiming, is not just understanding how you are solving a problem or fulfilling a need or improving a bad situation. You also have to think about, how could I potentially cause damage by trying to help? And is it worth it? And it's important to be aware of that. Even if we do go ahead, right? It's important to be aware that we are choosing one value maybe over another when we produce a new system. So with this framework, you can teach how to describe an existing system, but you can also teach how to design a new system. And I want to be very clear, this is not a framework for designers and for engineers. This is not something that I'm suggesting to use in industry. This is a way of teaching what I call introductory systems thinking. So how to introduce systems thinking to students who have no idea what it is. Never heard of the term before. So I heard the term systems thinking for the first time in the second year of my PhD. So if you teach this to your students, they will already be in a better position than I was. But you can use the framework to describe a system, and then you would start with the architecture, then describe the function, then describe the purpose. The purpose is the problem, the stakeholders, and the benefits. That's what the purpose is altogether. And then the detriment. And you can just ask them to just do, one detriment or one purpose. Sometimes systems have multiple, right? But multiple purposes, multiple detriments. But we don't have to cover everything. We're trying to focus on the major, essential, most important ones. You can also design systems using this framework, or teach how to design. But here you start with the purpose. So you start with, okay, who are the people that we want to help? What is their problem? What benefit do we want to provide them? Now let's think, okay, what function do we need? So what kind of system of interest do we need? What kind of architecture do we need? And finally, also think of the detriment. So the detriment always comes last. So again, the idea is that you can build assignments where students can engage with describing systems, designing systems using this framework. And I'm going to show you some examples. So describing a system, so how to teach. So there are 3 ways that I can recommend. And it really depends on what you teach and who your students are and so on. One of them, you provide your students with one system. They don't have a choice. Let's say a bicycle, right? And you can even provide them with all the information. So what I do sometimes, for example, I give Wikipedia articles. And I tell them all the information you get from there. If you can't find something, like for the function and for the outcome or whatever, let me know. Sometimes I even create myself an article for them, like 3 pages, and I know all the information is there. It's not, I'm not doing the work for them. It's not written like as the framework, in that language. It's written in a normal, Wikipedia type or academic language, but they can get all the information from there. So one way of doing this is just to provide the students with the system. Another one is to provide them a list. This is what I usually do. The students are a little bit more motivated that way because they have a choice, but at the same time, I can control the system is not too simple, it's not too complex, it's just right. So I usually give them like 4 or 5 Wikipedia articles. So one is about like a train, like a fast train, like they have in Japan, for example. Another one is about instant messaging app, like WhatsApp or Telegram or something like that. Very different types of systems, just to show them like that they can think about software or hardware or mechanics or very big systems or very small systems. They can think about all of these as systems with systems thinking using the same principles. And finally, students can select their own system. Now, this is very good for motivation, but of course it presents a difficulty because it might not be appropriate, there might not be enough information about the system, it might be too complex and so on. So now I'm going to show you an example, again, with a bicycle, with a relatively simple system. Bicycle is not that simple, I can also show you with a pen, how to do this. And a pen is an even simpler system. But a bicycle is a good introduction, and if you can bring a bicycle into the class, for example, even better. So we've got the architecture here. As you can see, I used the red color. And I didn't write every single part of the bicycle. That's not the idea of this framework. The idea is just to choose the major parts, okay, that I think are the major parts. And this is a discussion with the students. The best thing is to do it in teams. So the students are in 2 students, 3 students, 4 students, and they have this discussion. So you can see we have the parts and we have the interactions between each part. So this is the architecture. And I use the red color to say, okay, this is the architecture of our system of interest. And now this is the function. So the function is a blue color. And as you can see, I have 2 other systems. One is a biological, natural system, which is the human cyclist that provides input into our system of interest. And the other one provides output to the network of lanes of cycling where everyone cycles around the city. And as you can see, I use blue color for the function. And also, I did not detail the architecture of the boundary systems, of the input system and the output system, because it's not important for us, because our system of interest is actually the bicycle. But this shows us the function. So this shows us how the bicycle actually functions. And finally, we have outcome. So what I did here, I took everything that's here and I put it into structure, behavior, input, and output, as you can see. It's exactly the same text. And finally, the system outcome. So who are the stakeholders? So these are people who live in a city and they live outside a city center. The problem is that walking takes too long and car is too expensive. The benefit is that they get faster and cheaper transportation. So that's the benefit of a bicycle to these stakeholders. But the detriment is they are more vulnerable to dangerous accidents. So if you are in a car, you are more safe. And if you just walk, you are not very fast. So you're not likely maybe to get to as many accidents. So again, this is specific. Some other stakeholders, other groups may use a bicycle for other reasons. And they will have a different problem and the bicycle will have a different benefit for them. Now, I know we don't have much time, so I'm going to skip over the next example, but I just want to show you that it's a very different system. So this is a coal-fired power plant. So this is a coal plant, right? A lot more complicated and a lot bigger and just a very different type of system, but you can do exactly the same thing. Now, you don't have to use, I used your Canva, canva.com. You don't have to use digital anything. You can do this on the board. You can do this with a piece of paper. You can do this in PowerPoint. As you can see, it's really simple block diagram. Again, exactly the same idea. Again, these are just explanations. Now, there is, as I said, a very detailed assessment for all of this. So you can actually go through the students' diagrams, right? So if they are, you tell them here is a coal-fired power plant, here is a Wikipedia article, read the article, go through the article, and map it into the SAFO framework, into this framework, SAFO, and they come up with these diagrams, and they fill this out here. You can actually assess it. So you can assess how well they followed the framework, how well they followed the instructions, and you can also assess how correct they were based on the article you gave them. Now, these slides don't show you everything. If you want to see everything, go to the article. It's very detailed. By the way, to see if they follow the instructions, if you have access to generative AI like ChatGPT, ChatGPT or Copilot or whatever, you can use it for that as well. I would not use it for correctness because I would not trust generative AI, ChatGPT about correctness. But when it comes to following instructions, I would, because the instructions for assessment in this framework are very detailed. We did a lot of work, very, very detailed. So all of this, structure, behavior, input, output, stakeholders, problem, benefit, detriment, it has specific instructions on how to assess. and it can get either a 3, a 2, a 1, or a 0. The numbers don't matter. It's just about the feedback you can give students to then improve the work. Okay, so it's not about giving a grade, but it's about improving the work afterwards and giving them feedback so they can improve. Now, as I've said, you can also use the framework to teach how to design a system. And here is the same. You can provide the students with one purpose. Everybody works on the same purpose. So this is the group of people you're going to help. This is their problem. And this is the benefit that your system needs to deliver. You can also provide them with a list of purposes. Or you can ask them to come up with their own. So again, up to you and your students and what you are teaching. Now, how to choose problems. You can actually have two sources. So in the system, in the framework, we have what's called a problem, right? Which is what our system of interest was designed to address. Okay, so a bicycle was designed to fulfill certain needs, solve certain problems. But there is also what we call the detriment, if you remember, which is the problem that our system might cause. We can also take that and use it as a new problem to create a new system. And then it turns into what we call a problem in the new system. So here is an example of designing a system. It's a little bit complicated, so I won't go into it now because I don't think I have a lot of time left. I think I have about 15 minutes left. Is that right, Diane? Do I have 15 minutes?
Yeah, you've got about, like 10 minutes.
Okay. Okay, no problem. So this is an example actually quite early on. So this is about a year and a half after I began working and developing this framework. So this was done with undergraduate students, not first-year students, undergraduate, but not first year. I believe there were second and third-year students there. And I gave them the purpose. So the capital of Mongolia, the country of Mongolia, is the coldest capital city in the world. It's also the most polluted. The people there mainly use coal. They burn coal during the winter to heat up their home. And at MIT, they developed an alternative solution that is not polluting, which is this brick. It's basically salt, and it's heated up, very, very hot. And the idea is that it's inside steel. It's like a shoebox. It's about this big, and it gives off heat for about 6 hours, 8 hours during the night. So it's a good substitute for coal. The problem is it's very, very hot. Okay, it's hotter than burning oil, than boiling oil, and it's heavy. It weighs over 10 kilograms. So you can't just carry it and throw it, and you have to be very careful. You have to think about how am I going to carry it around. So I gave this problem to students, and again, I'm going very quickly here, but they use this idea of, okay, this is our purpose, so this is the function, this is the architecture we want to build, and so on, to think of ideas, which, as you see, this trolley that they came up with, where there is a little opening in the fence, usually for trash, for garbage, that somebody can come and they have all the equipment to carry this brick, and they put it on the trolley, and the trolley is on the side of the house, and then they take it inside. So again, this is an example of designing a system with a framework. And finally, we can also connect systems. So if you remember the title of this talk, I was talking about connecting between disciplines. It's not just disciplines, it's domains, it's organizations, it's roles in the organization, and just people. And this is something that I've only really started working on about a year and a half ago with my colleague from Aalborg University. And we have been using this framework to get students from different disciplines to explain their projects to each other. And what they do, they try and find, okay, this is my system, this is your system. Let's try and find a system that connects them. Or maybe there's two systems through which they are connected. Or maybe there are three systems, right? And they do this exercise. So here I want to show you an example. So on the left, this is something I already showed you, which is the bicycle. So we have the architecture in red and the function in blue. And on the right, I have a car, just a regular, car that drives on petrol, And the same thing, we have the architecture in red, the function in blue, But as you can see, I also have connections between them. So one of them is that some of the lanes are shared between bicycle and car. Okay, so this is actually a joint system between them that connects these two functions. And also the human cyclist breathes in the air of the city, and the air of the city is being polluted by the engine of the car. So that's another connection. Now notice something interesting, which I did not mention up until now. In this framework, you can very easily zoom out and zoom in. What do I mean? I can treat the function of the bicycle as an architecture. I can say the human cyclist and the bicycle and the cycling lanes all together are a system of interest that I want to look at. So they would all be in a red border, right? In red color. So if I'm like a city planner, someone, you know, who plans cities and how the roads will go, that's how I would look at this. I'm not interested in just the bicycle, right? I'm interested in how the different bicycles and the people and the cycling lanes, the roads are interacting with each other. So I can zoom out. I can also zoom in. If I take the car, for example, the architecture of the car in red, I can zoom in on the engine, on the internal combustion engine, and say, this is now my system of interest. I want to create a better engine. I want to understand what parts the engine is made out of. And then the car would be the function or the environment. Okay? So you can zoom in and zoom out too, which is a very useful exercise. And again, the idea here is that you can have each student or teams of students independently map a system, and they can be very similar systems or very different systems. And then they get together, they explain the mapping to each other, and they try and think of, okay, what systems can we find that connect our systems? And these are ways of explaining to each other our disciplines. So if I'm working, for example, on microbiology experiment, and you are working on optimization algorithms, maybe there is some algorithmic or software or data analysis component of my experiment in microbiology that we can then link to what you do. And then with that new object, with that new system, is something that we can both explore together and we can both contribute to. And then better understand what the other person is doing. So I really threw a lot at you, I know. As I said, I sent Diane all the slides. I just want to point out all the references are here. There are two things which I would love for you to check out. There's my email. There's a problem-based learning platform that includes some of these ideas as well as other ideas. It is free to try if you are interested in doing more active learning, problem-based learning with your students. And maybe you just don't know where to start, or you're not sure about it, how much work it is. This platform has a research-based methodology, very structured. It has assessments for every step. It has a very clear structure, has student reflections, very detailed instructions. I'm, of course, very happy to explain. And it's funded by an internal grant at MIT. So if you want to check it out, please let me know. You can go on this website. Register is invite only to register. So you can just email me and say, Rhea, I want to see what this is, and I will create a project for you, and you can just check it out. You don't have to do anything with it. You can just see what it is and ask me more questions. And if you're interested in trying it with your students, let me know, and I'll be happy to follow with you, and we can do that together. And finally, if you want some assignments, examples of actual assignments that I gave my students, my first year students, you can go to MIT OpenCourseware, OCW here, and there is actually all the materials, nearly all the materials from my class, and you can just try them out and try them yourself. And that's it. The other materials we don't have time for. So thank you so much for your time. By the way, I see that I need to change this link. This link is not correct. So Diane, I will send you a corrected slide, corrected presentation right after my talk. But yeah, I'm done. So if we have any time for questions, I'll be happy to take them. Thank you.
Sure, don't worry about the link. It can all be done. I thank you very much, Rhea.
You're
It
welcome.
was very, very interesting listening about systems, because some people don't really think about what's behind solving a problem, for example. And like, there's a lot of steps that we can take, we can adopt from engineering that will help us think more like a programmer or an engineer in order to solve problems by steps, and just try to take it little by little. And it was a very, very good insight. I don't know if we have any questions. ¿Alguien quisiera hacer una pregunta? Ay, Rea, people in Venezuela are very, very shy.
Oh, that's
I,
okay.
but I do have some comments.
Mhm.
I used to use complicated and complex as synonyms, and it turns out they are not. So
Mm.
it was very interesting. Like, hey, I've been using this wrong. And also, Bloom taxonomy is taught here at the university, but we didn't know about Anderson. So it's
Mhm.
something we can take away from your talk. And everything else, everything you say about Sappho, how to take the systems one step at a time, um, and it was amazing.
Oh, thank you so much. So yeah, just a couple of things, about the complex, complicated thing. It's not that you're wrong. It's just that some people make that distinction, and I think it's a useful one, because we can have a system that's complicated but is predictable. So again, like a refrigerator. A refrigerator is not a simple system. Once you actually get to how it works, I don't really understand how a refrigerator works. That doesn't mean that when something goes wrong, I don't know what to do. There's a technician, or and the technicians will know what to do. But if we take something like, I don't know, say a university, right, or say something like a complicated a car, even, okay. Sometimes it's actually very hard to know what goes wrong, when there's a problem. So, and there's an unpredictability to the interaction that goes on. So that's kind of the difference there. And in terms of using Sappho and so on, to me, the important thing from this talk, what I want people to take away, are really like the principles of what I'm saying, which is, when you are, firstly, that systems thinking is important, and it's important for everybody. And that if you want to teach systems thinking, what you want to teach is not just what this pen is made out of and how this pen works, but also what makes this pen function. Because if we don't have an appropriate surface to write on, and if we don't have the hand or something similar, that knows how to use it and can use it, the pen will not work. So it's not enough to just understand the pen. We also need to understand the point of interaction, or the points of interaction, with the boundary systems, which is the hand and the surface. And this is true of anything. If you want to understand how you're teaching, how your group of students, or how anything, an assignment, is going to be successful, try and think of the boundary systems that it's going to interact with.
Yeah, and I also think it's about zooming in and zooming out,
Yeah.
which is very important, because you said you can take all the parts of the bicycle, or you could take the bicycle as its own, or you can take a part of the bicycle and make a system just about it. And it
Yeah.
was it was just another point of view on how to look at systems.
Absolutely. So the zooming in, zooming out is also very, very useful, because you can look at your assignment as a system of interest and what it's made out of, but you can also zoom out and look at your entire course as a system of interest. And if I want my course to be successful, there are other things it needs to interact with, like certain technologies, maybe other instructors, maybe I have an assistant, the physical classroom, So again, these are just principles, and if anybody wants to get in touch, I'll be more than happy to.
Thank you very much, Rhea.
You're
It's
welcome.
been amazing having you here. I'm sure everyone will ask me for the presentation later on. So I'll be sure to just tell everyone about it, tell everyone about how the ways of contacting you, because I'm sure more than one will be very excited to get in touch once they read the whole presentation. So I thank you very much for taking the time and for being here. It's very special that you're taking part in Venezuelan education. And well, here we are, one talk at a time.
Thank you so much for the invitation to the university, and to you, Dayan, for facilitating this, and to everyone who gave me their attention. Thank you very much.
No, thank you. Bye bye, Rea.
Bye bye. Take care.